Hello, my name is Hugh, Pierre, and these are my teammates.
Mohammed, Alali.
Kristopher, Chung.
And this is our senior design project for our hydroblade concept. The problem that this addresses is that many rural areas, especially those in third world countries, are constantly without reliable sources of power, but are surrounded with natural elements that normally produce electricity, but that goes wasted, and we aim to relieve that error. The way that that our system works is that we have adapted piezoelectric technology to take advantage of the normally wasted vibration energy that occurs with the surface of certain bodies of water. Just to give a little backdrop into the inspiration for this is that I did an internship in Bluefields, Nicaragua with a company called Blue Energy. And what they do is that they promote green living in third world countries like that. And while I was there, in this area, there are towns and villages that are not connected by roads. People and freight are moved through the waterways, tributaries, deltas, and even parts of the sea. And while I was there transporting parts for a solar panel in a jungle community, I just made note of the waves that were crashing into the shores, the jungle bush, and even along the docks. And I thought that that's energy that's on site that can be utilized by people who already live there. And the aim of us is to build that system that stores at minimum 5 volts of electricity that can be used to power energy efficient lighting systems within a person's home. And this image here is just to give us a sample of what's happening with our product. A laminar flow will be moving towards the airfoil, and at a certain point above and below, that laminar flow will break and become turbulent. And that turbulence that occurs along the tail end would have different pressure areas, which would cause an oscillatory motion along its tail, which would displace the piezoelectric element, which would be attached at this end, as the airfoil matches into the tail. Theoretically, what we were aiming to do was to increase the drag of the airfoil, but still allow for the water to flow where we wanted to. And a lot of the theory says that a lot of that would be out of our control, such as in the density of the fluid or the speed that the source would be moving at. But what we did have control over was the area by which the flow would be hitting our airfoil. But in the laboratory experiments that we did, we were confined to 6 inches in width because of the hydraulic channel we use can only fit a product of that size. And this layer is just to give a comparison of our draft coefficient of our airfoil compared to other objects and shapes. We were researching how we might artificially improve on our efficiency. Came across a company in Spain called Vortex Bladeless, which built this bladeless wind turbine that has been completely redesigned to be a conical tower with pits all along its surface. It utilizes a little known property in fluid mechanics called vortexicity, which is just the study of the formation of vortices of differing strengths and intensities all along the surface. And for what they did here, this tower here would wobble as the wind speeds strike it and generate electricity at the base of the tower. And we look to adapt that technology, that principle, into ours. And to help us do that, we had used a hydraulic channel on various frequencies and velocities. And the Strudel number helped us to determine when we were either straying or keeping to the path. As a general rule, as the Strudel number increases, as the frequency increases, the velocity increases, the Strudel number also increases. And to go more into the design aspects, we have Mohammed Alali.
Thank you, Hugh. I'm going to elaborate more about our design process. We started with an idea of having a board connected to electromagnetic induction on the site. And once the water or the wave goes over the board, makes an oscillating motion that generates electricity with the electromagnetic induction over here. But we found out it's one, the electromagnetic induction is very heavy, and also the board is too long. So we developed the idea to this one, which is a smaller board, and we figured out to use another way to generate electricity with piezoelectric. So we designed to have the board with the piezoelectric all of it on top, but the problem was also it's hard to deflect it, and it's also practical to 3D print this part. So we developed it to become our project. We have airfoil here, the wing, connected to a piezoelectric material, connected to a tail with weights to make this displacement and generate electricity through it. As you can see here, we made also simulations plan, most importantly about the deflection, and we got a max deflection of 0.3 millimeters, which is really considered good from the point of the attachment to the beam. The unique features of this design, we have the tail orientations, which allows to have different orientations of the weights distributed in many ways. And also we have the pitted surface, which encourages the laminar flow to go over the surface. And also the sharp angular change at the end, which also helps the fluid to move faster over the arc surface. These are the tail orientations. We have the L, the I, the triangular, as you can see them here. And the triangle was to increase the surface of the area to help with the impact, and the I was acting like a beam, so the displacement can be easily measured, and also the L was favoring one side from another to make the twist and to which make a better displacement motion. We have the sharp angular change at the end over here, which also helps the velocity to encourage it, and also the tumbling of the flow, which increases the eddy currents, which also helps with the oscillations at the end. This is our mounting for the design, which we use PVC pipes. And as you can see in real life here, we realized after testing it in the field that the angle of impact is really important and crucial to the results. So we developed it to become this one in SolidWorks, which you're also going to see in the next slides. This is our final design from the top corner view. This is the wing with the piezoelectric material and the weights, and this is a close-up from the right angle. Let me tell you more about the results, since this is what really matters. First, we did it in the lab, in a hydraulic channel, and keep in mind this hydraulic channel can only generate the weight for 5 seconds only. So with the results we got, we made many trials, and the average was for the I over here, and the L orientation, and also the triangular. And you can see them also in the graph. And this is the field results for the first one, which is the I. We can see the trial 1 was for the calm spot here in the blue, which is really good, and also the trial 2, which is negligible wave action. You can see it barely made anything, and trial 3 was generated beyond the scope measuring. So it looks really steady. We also did it for the L orientation. Trial 1, we had a really good also result in the calm spots, and trial 2, the greater disturbance, we had a very good results as well. And trial 3, the negligible wave barely made anything. Now we showed you the lab and the field. Now we're going to compare them together. And keep in mind I said 5 seconds, so we calculated to be 5 minutes, so it can be fair to the field. We have the I orientation for 5 minutes, the L, the triangular, and of course we don't have a triangle there because we figured that it barely made anything in the lab, so we kind of neglected to do it in the field. Now with my colleague Kristopher.
Okay, thank you very much, Mohammed. I'll now speak a little bit more on system deployment of our prototype. Okay, so although we plan to use it in areas with low hydraulic head, and where there is a constant flow, constant running of water, we plan to deploy our hydrobladed masses because of how expensive, two, how portable, and how light it is. And we really plan to reach a lot of people, especially in urban, rural areas where there's not readily access to electricity. Okay, so here you can see a video of us testing it on the field. Here you can see calm conditions, and then you see one wave, and then another wave past it. This was taken in the Miami River, and all the data that you saw prior to this slide here was taken from conditions like that. So we plan and we hope to test these in conditions not only like this river, but also places with a lot of tidal streams, when action on the surface, waves passing from boats, not only boats but other conditions as well as underwater currents. This is a cost analysis of what it costs us to build our prototype, and you can see it cost about $400. Okay, so the main part we used for our design was a piezoelectric material. And this piezoelectric material, these have been used a lot before, not only for generating voltages, but also in other applications. Some noticeable ones may be electronic frequency generator and detector, and some more everyday ones could be like a push starter in your barbecue pit, as well as in quartz watches. Okay, so conventionally harvesting energy required a lot of resources, a lot of manpower, a lot of time, and definitely a lot of money to construct things such as dams. And these have also had a lot of adverse effects on the environment. So this is where we hope to come in and change it a little bit, making it a little more cleaner and more accessible to everyone. Okay, conventional, as I previously mentioned, conventional methods have been very expensive. So this is where we hope to make an impactful help to the society by providing cheaper sources of harnessing clean energy. So as the population continues to grow every year, so does the request and require for energy, electricity, and so for clean electricity. So this is where we hope to make a worthwhile contribution to society in our project. Okay, so I think I can safely say after doing this project, we really understand that there's a real need for clean energy today that are not only for certain kinds of people or certain pockets of people, but readily accessible to everyone and for a good price and for everyone everywhere. Okay, so in concluding, I would just like to make note that the three configurations I previously mentioned, the I1 proved to be most effective, most efficient, producing a voltage between 1 to 8 volts. Notably also, the L was quite effective, but produced a little bit lower, giving us a range between 1 to 4 volts. Okay, so what was previously described to you was basically one of these nodes that you see in this whole diagram here. For the future, this perhaps may be something that we can look at eventually. Here you see 12 of these devices set up in a system here. And after doing calculations, this is calculations from what we got in the field. We came up with a range of voltages that we could probably get per day. And for the range goes from 3,450 to about 17,300 per day. So that's bearing in mind, we're taking the results that what we achieved in the field. Okay, so in future, we'd like to work with more inexpensive and different manufacturing process to probably increase the efficiency and effectiveness of this prototype. We'd like to introduce this prototype to companies like Blue Energy, as Hugh previously mentioned, back in Nicaragua, where they do a lot of energy work across there. We would like to add more piezos to customize it, again, try to make it more efficient. And lastly, we'd like to incorporate this concept into flagrings, where we believe there's a lot of energy that goes wasted. So we hope that we can probably apply this to harness that energy. This is the work plan we work with throughout the both semesters, responsibility of each member, and lastly, our poster. Thank you very much. That's it for our presentation.
On one of your slides, you talked about, could you go back to the slide that has 12 lasers? Some? There you go. Okay. You're presenting it as 3,456 volts per day.
This is based off of assuming that the conditions would be ideal, because we in the field, each orientation had like 3 trials. We had found, and these were timed so that time during certain parts of the day where we felt that there would be most wave action. So these are based off of ideal assumptions, which we know wouldn't be consistent throughout the day, and they vary from
How much power do you actually get?
From the field experiments, we got like between 5 or 8 watts.
So how do I translate that to watts per day?
We didn't bother with doing that for this because we thought that because this is based off of ideal conditions, it wouldn't be a fair representation of what would come up to it. We just made this to show that we want to create it into a system that would line the edges of
Okay, so would you take this energy into batteries? Would you
yes,
take
the
this
idea is
into
to
an
put
AC
it
circuit?
Yeah, because it's oscillating, there would be instantaneous moments where it's generating a voltage and when it's not. So for it to be useful to appliances specifically for lighting systems or to charge small devices, it would have to be stored in the battery, and then that battery could be used in that capacity.
Okay. Thank you.
Thank you very much.